Greetings, friends. We are going to continue on talking a little bit more about wave functions today and doing some qualitative reasoning about their shapes. We're going to finish off with the infinite square well and the potentials. So once we get that done, then we'll talk a little bit more about what the wave function looks like for different potentials. Alrighty, so in this case then, what we're going to start off with is well, first I guess what we can do is remind you that there are a couple of things due today, so let's go do that. We have PLC 14, but that's tomorrow, Friday. And we have homework 8, which I believe is due today. Plus, there's a quiz up and running, so that would be quiz number 6 or 7 or whatever it is. I don't remember what it is. And the usual deal on that quiz, you may use open book, open notes, but nothing that is outside of that, okay? So that involves no using computer, internet stuff, sources that are outside, of what you've created for this class. So usual deal, that's going to be a 1 hour, 60 minute. 60 minute is the base time. So please be aware of doing the usual, making sure your internet is stable, making sure you had enough time, you've submitted your homework, you are good to go, and deep breath and off you go. Alrighty? All right, so we were talking about the infinite square well, and I left off talking about probabilities. Oh, by the way, before I do that, homework 9, okay, homework 9 is going to be posted, but remember not to be turned in. So I will put up problems in homework set 9 that would be normally homework set problems that would get you ready for the final, but I'm not going to collect those. And that means our final, I believe our final is going to be the Wednesday, the 28th, 29th, 30th. 31st, I believe it's the 28th. Let me just take a quick look on the syllabus here and see if I can just find that real quick and make sure that I'm getting this right, because I don't think I've announced that yet. Yes, Wednesday 5/28. So it'll be the same type of deal with the final as it was with the other ones. In other words, you'll have the day to pick your time block, sit down all the way through and be done at any point on that Wednesday, all right? I will alert you to the fact, however, that it is written and expecting that we have a 3-hour time block, or should I be precise, say 2 hours, 50 minutes, probably just gonna give you the 3 hours to do it. All right, so this is gonna be a 3-hour time block. And will be written for 2 purposes. Number 1, to review all material prior to celebration 2. In other words, it's a review of things on celebrations 1 and 2. And then the other part is to then be a celebration on the stuff since celebration 2 that we've been talking about. And that includes all the modern stuff. So special relativity, quantum mechanics, and that's going to be it should be about half and half. Okay, so we were talking about the infinite square well. Let's continue doing that after I messed up the normalization integral, but I know where we were going anyway, so I got the integration wrong last time, but I'm going to have to go back and redo more of that integration. So problem here is that we know the potential, okay? So the potential, if I look at that, is all right, up to plus infinity here, and up to plus infinity here, and 0 otherwise. This was x equals 0, this is x equals L, and so we found that the particle is confined within here where the potential is 0. Oh, I shouldn't put 0 outside, that's the wave function, sorry about that. V equals 0 here, sorry about that, V equals 0 there. And it's infinity outside that, got that wrong. So the wave functions made by the particle then correspond to a continuous function in which the wave function is 0 outside here, but then adopts standing wave patterns inside the well itself, all right? And we found out that the standing wave patterns were just sines, and they look like this. This is n pi x over L. And so our entire wave function ended up looking like that. And the energies that correspond with that wave function ended up looking like, if you look at the simpler form, I guess it's h squared over 8ml squared times n squared. Okay. If you reduce the h bar squared pi squared piece that I did last time, it would look like that. And so the function that describes the wave function of the particle inside the well is something that goes to 0 on both ends and adopts a standing wave, excuse me, adopts a standing wave pattern on the inside. And so we sketched out a few of those and found that inside here, you'd get something that might look like the jump rope pattern is typically what I call that. And then this is the n equals 1, and then the n equals 2 would have this type of thing going on, and the n equals 3 would have 3. So what you do is you look at the number of bumps it has, and that's basically the same thing as the principal quantum number, right? The jump rope has 1 bump in it, this has 2 bumps in it, and so that's the 2 state. That's how you can figure that type of thing out. Okay, other hallmarks of this are to note that the ground state energy is not 0. There is some energy. That means any confined particle will always have some kinetic energy, which means that you can never actually confine a particle and then get it to be at rest. A quantum mechanical particle will always have some what's called 0-point motion, because it will always be jiggling around as long as there's some confinement that we're trying to attempt. And as we found with light, the more we try to confine it, the more it spreads out and becomes more uncertain. All right, so we had left off talking about probabilities, so let's just do one last calculation for completeness' sake here, in which I want to find the probability of finding the particle between 2 quarter points, between L over 4 and 3L over 4. And let's assume that I am in the n equals, let's suppose that I'm in the n equals 2 state for this, all right? Well, no, let's do the n equals 1 state first. That'll make it easier. All right, so what I want to find is the probability. That's too many of those. Probability of the particle being found between the 2 quarter points. In other words, in half of this right in here. All right. And I am going to use the n equals 1 state. Okay. In the previous video, I quite well messed up the normalization integral. It is what it is. However, what we did from that is we demanded that because the particle's wave function is 0 outside this well on both sides, that the particle must be found just within the well. So that when we looked at the normalization integral, instead of going from minus infinity to plus infinity, we only need to go 0 to L, okay? Then if we only go 0 to L, we do the integral, and that's the one that I didn't get right, but ultimately it tells you that the entire probability of finding the particle between 0 and L has to be 100%, because that's where it's going to be. It can't be outside that. The wave function is identically 0 there. In order to find the probability of the particle being found between two other points that are smaller than 0 to L, all we have to do is the same exact integral, but just with different limits. So if you look back at the if you look back at the normalization integral, it looked like this. It looked like 1 equals integral 0 to L of a squared sine squared n pi x over L, and we were integrating that dx. This is guaranteeing that between these two limits, we have this probability of finding the particle. All we have to do then, in order to change it so that we can answer this question, is we change the limits to what we're interested in. We integrate the same exact thing, but now we're interested in what the result is. We don't already know what the result is. So in the case of normalizing, we are forcing the particle to definitely lie within two boundaries, okay? So whether it be minus infinity to plus infinity or 0 to L, whatever it is, we're forcing the particle to definitely be found within that. But now we're asking, okay, out of that 100% of finding the particle here, how much is it going to be, what's the probability of getting it within there? All right. So essentially it's the area underneath the n equals 1 curve there. Okay. So now that we have the full wave function, all we have to do for this is alter it a little bit and say that this probability is going to be equal to the integral of L over 4 to 3L over 4 of the full psi squared, which we know now, integrated dx in those limits, okay? The point of doing the normalizing was to actually find what the constant out front is. Essentially, it sets what the amplitude of the waves is, okay? It sets that amplitude. That's what the normalizing procedure is. That's what it's for. Now that we have the a squared and we have the full set of wave functions, then we can just go straight to integrating it between these limits. All right, so what that means is, that we're going to take that probability and say, if I square the wave function, it's going to be this here. So I'm going to have 2 over L sitting on the outside, because that won't play a part in the integration. L over 4 to 3L over 4 for my boundaries. And then I'm going to do that exact same sine squared integral, the one that I thought I had last time but didn't. And in this case, n is equal to 1, because I want the probability in the 1 state. So this is just pi x over L dx, where n is equal to 1. All right. So I think I had this. So this one is going to be equal to then x over L minus 1 over pi sine pi x over L cosine pi x over L. And now I have to evaluate that between L over 4 and 3L over 4. Okay, I think that's what after last time I went ahead and looked at that, and so I'll go make sure I got this one right. I think I got this one right. So I guess I'm not sure if I got it right, but I think I got it right. Yeah, looks like I'm going okay here. All right, okay, we'll see how we do. Now, if I am going to evaluate this, let me just erase that so we can get a little bit of a space here. Okay, if I'm going to evaluate this, then I'm going to do 3L over 4 in the x, which means I'm going to get the value of 3L over 4 divided by L, so that's 3/4, minus 1 over pi sine of 3L over 4 in here. If I do the 3L over 4, that's just 3 pi over 4, right? Yeah, that becomes 3/4 pi. And then this becomes the cosine of 3/4 pi. And then I have to subtract from that. That's the 3L over 4 analysis. And now just the L over 4 becomes 1/4 here minus 1 over pi. And now I've got to find what the, now I've got to find what the sine and cosine is for this. I'm going to have sine of pi over 4 and cosine of pi over 4. Like that. Okay, but these are all just pretty straightforward numbers that we can calculate, and they shouldn't cause too much of a problem. When you're all said and done with it, what happens is we end up with the 3/4 minus 1/4. That's going to give us a half. Okay, and then you're going to look at what happens with the 1 over pi as well. 3 pi over 4 and 3 pi over 4 and pi over 4 and pi over 4. So what it ends up being is, it turns out to be a half plus 1 over pi, which is about equal to 0.82. Alrighty, so this is the, let me get this back. All right, so this is the probability of finding the particle between these two limits in the ground state, in the n equals 1 state. The good news about that was that we kind of had already done this integral, even though I screwed it up last time, and so it should be pretty straightforward to do it again, and then just reevaluate the upper and lower bounds on the limits. All right. Okay. We would expect this to be a pretty high number. You can see it's 0.82, and that's only between the 1/4 and 3/4 points. But for a function in which it looks like the first half of the sine, right? It's going to have little bits here and then a huge peak in the middle. I haven't drawn it really to scale quite well here, but the area of this shaded piece here compared to the area of that and the area of that. So this is 80% of the area, and it's left with 10% on either side, which seems probable because the sine is quite well peaked in the middle. Okay. All right, so that's how to find probabilities. We talked about normalizing last time. We talked about solving last time. So what I want to do now is say that we're essentially done with this example. The example of setting up the Schrodinger equation based on the potential, based on the V that I had, which was, I just chose the simplest one. I think it's the simplest one. Solving it, looking at what the boundary conditions are, making sure that the wave function is continuous. Solving for the energy states. After applying the boundary conditions, that's where the quantization comes from. So applying the boundary conditions makes the quantization condition. Once I find that quantization condition, I realize the energy is quantized, finding all those energy levels, and then looking at the spectrum and what the allowed energies are, then what the wavelengths of the emitted photons are going to be, and then looking at normalizing, figuring out the entire wave function, and looking at probabilities. So all of that stuff together is basically the example for this for this situation here. Now the question comes in: what am I going to expect you to be doing? Well, that seems like kind of a lot. So what the things that I want you to concentrate on are looking at what the spectrum looks like, right? We came up with the energy levels, and we wanted to look at what the wavelengths of the emitted photons were going to be. So thinking through that process, okay? I went a little bit above here, but nonetheless, for other potentials, this process can become quite cumbersome. So I'm not going to really ask that you do anything different or worse than this. But what I do want to think about is, okay, well, what if we took this and narrowed it a little bit? What would happen? Or if we expanded it a little bit, what would happen? So to answer some of those questions, we can look at what the qualities of the wave function are going to be. And to do that, I want to show you, let's see if I can do a quick screen share here. I want to show you this here. How do I do that? I do that by doing this and then this. So hopefully you can now see my screen, and it's on this website called ridiculousfish.com, which I think is great. I happened upon this last semester when I was teaching the modern physics class, and I just had typed in something like wave function visualizer, and I got to this place, and this is pretty dang good. So what it lets you do, I'll just go through some of these things here. What it lets you do down here on this set of buttons, the V is you can choose a potential. Okay, so for example, I can choose a simple harmonic parabolic potential, the infinite square well we just got done doing, the finite square well we're going to talk about, two square wells, right, or like with a barrier in between that could be infinite or not. I mean, the wells could be infinite or finite wells. Stepped, so if it's slightly up, slightly down on two levels, something random. Wow, that's pretty random. Okay, I was not expecting that. Okay, those are gross. We're going to go back to the infinite square well here. You can see these buttons. You can choose to click these buttons so that you see, for example, I want this thing to show me the wave function. You click the wave function button. Actually, I want to see the probability. That's going to be the square of it. Point there, it looks like this. These two are not going to apply to us. They're momentum wave functions. We haven't talked about that, so I wouldn't worry about it. This is, I guess, showing you how it's evolving with time. Also something that we haven't talked about, so I wouldn't worry too much about that. And then what's this one do? Oh, this one flips it around so you can see things. Okay, so you got to zoom in and zoom out. Okay, all that's great. But here's the really cool part. You can change the energy level that you have, right? So you can change the energy level of the electron or whatever particle is in here, and you can change the size of the well. Okay, so for example, putting something into the 4 state. How do I know I've got the 4 state? I should have 4 bumps. So, like so. Now, real quick question. Let's see. I've got 4 bumps here, right? 1, 2, 3, 4. Still got 4 bumps. So why is this not the n equals 4 state? Careful analysis of what's going on at this boundary will give you the answer to that question. And you can see that as you pull this energy up and down, strange things happen, right? You see this this line right here. What that's telling you, and furthermore, do you see the kink that is happening right here where my cursor is? The kink that happens is telling you something. It's telling you, watch out, this is not a physical wave function. We don't want kinks in the wave function like that, all right? We want it to be nice and continuous so that when I think about the boundary conditions, I want it to be going to 0 over here on the left, like it has been doing very nicely. I also need it to go to 0 over here on the right. So therefore, this is not a valid wave function that will be supported. If I give something a wave function that looks like this, it's not going to last for very long. Okay? Now, how do I know when I've gotten to the appropriate wave function? I know when it looks like that on both sides. It's nice and continuous, right? No kinks. So if I go, and this program will solve for any energy level you want to give it. It won't tell you which ones are the proper ones. You have to look at that. So you take a look at that. Okay, I got it. Now I go to the next one. No, 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 yes. Right there. And I go to the next one. No, 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 yes. Okay, so these are allowed energy states, the 1.54, and then I don't remember what the other two were. Okay, now suppose I go to the n equals 4 state, which occurs there, I think. Yeah, looks like it occurs about there. And I change the width of the well. What if I caused it to go to half of its size, or approximately half its size? Well, let's say it's about there. Okay, so now for that same energy, or near enough to that same energy, I am in a different state in the narrower well, right? I haven't changed the energy of the particle, right? It's still 2.52. That was my 4 state in that well. Well, the 4 state in that well becomes the 2 state in this thin well. What if I will go way out big like this? Well, that becomes the 1, 2, 3, 4, 5, 6, 7 state for this well. Whoops, right there. Right? So if I think about what the energy of the particle is, it's the same all the time. It just corresponds to different levels as I change the width of the well. So this is a really fun program. I encourage you to make some use of it. I'm going to give you some questions that will, in the homework set 9, that's not for turning in, I'm going to give you some questions in that using this will kind of help out a little bit. All right, so I just wanted to give you that and show you this because this is a pretty fun little application here. So enjoy that one. All right, so what I want to talk about today, or what I want to continue talking about, is what kinds of properties qualitatively can we assign to the wave function? If we want to say, I'm going to try and qualitatively sketch the wave function for some potential. Okay, this was a fairly easy potential. It was 0 all over the place. Okay, fine. But let's take a look at weirder ones, like that stepped one, right? There's one level here and one level here. So, for example, what happens if we look at that one? Qualitative. Okay, so what happens if I take a look at a potential that looks like this? And let's suppose it goes up to plus infinity on both sides. We could say that this is the 0 state here, v equal to 0 there. And let's just say v is equal to something over here, some number. Whatever it is, I don't care what the number is, but it's not 0. Likewise, you could have said that's 0 up there, this is some negative value, whatever. We'll just go this way. So in the context of, hey, I have a new potential, how do I kind of sketch out what I think the wave function might look like for this? That's what I want to get at. Oops, how do we guess the form? Right, I want to qualitatively make a sketch of this. What things do I need to look at? All right, well, there are a couple of things. And what I want to do is use, and this is why I solved the infinite square well so kind of thoroughly, because I want to use that as my guiding wave function. In other words, when I have a confined particle, like we will have here, I'm going to get standing waves. I should expect, in the sense that I have infinite sides here, I should expect the wave function to be continuous and equal to 0 on the outsides of the infinite well. Okay, we'll talk about the finite one in a little bit. So there are things that I want to highlight for you to look at when you try to answer a question like this. All right, so what I want to do is kind of give an outline of how to do that in the context of this problem. So how do we guess the form of psi? So we look at the Schrodinger equation. And I'm just going to call it the SE, if that's okay with you. Let's examine the Schrodinger equation and find out what it looks like. Now, what I want to do is take the tack that I did yesterday of rewriting it in a slightly more suggestive manner. So what I'm going to do is isolate on the left side the second derivative. Okay? Remember that this was a negative h bar squared over 2m, and then there was the d squared, dx squared. All right, we had all of that going. I'm going to multiply all that over to the other side. Okay, so what I'm going to do is, well, here, I'll do it up here. We have this. All right, so we have this. What I'm going to do is I'm going to subtract the v over to this side. Right, so now just the first part's equal to that. And now I'm going to flip the 2m over h bar squared and chuck it over to this side. So I'm going to end up with the thing I'm about to write right here, which is negative 2m over h bar squared times e minus v times psi, like that. Okay, so this looks very similar to the square well analysis that we did yesterday. The only difference is it's got the v in it, okay? Now, I want to talk about this. So, thinking through the solutions that we did in the last video, the one in which there was v equal to 0. Okay, we looked at that and said, I'm going to take two derivatives of this function. I am going to get back a negative sign, a constant, and then I'm going to have the function back again. So, wouldn't you agree the same basic thing is happening here? Because I look at the function and the second derivative, here is essentially some type of constant. Here's my negative sign, and here's the function back again. So the solutions should be pretty much the same things, okay? And that's why I did the infinite square well in detail, because I want to use that as my guide to thinking through more complicated potentials, but I don't have to actually solve these. I want to use that problem-solving guide as how I go through this, all right? So imagine this. First thing I'm going to notice is these had better be oscillating solutions. They had better be sine, right? Sine waves, sine standing waves, just like it was yesterday in the other one, because I have infinite sides here. So whenever I have infinite sides, I know the infinite potential is going to cause the wave function to be 0. All right, so one thing to think about is when you have the infinite sides, you know that the wave function is going to be going to 0 in those regions. And therefore, you're going to look at this term in the brackets here as some type of oscillating standing wave, all right? So first thing is, if v goes off to infinity, then psi goes off to 0. Okay? We have to match the boundary conditions, which means that we expect it to be 0 at both ends of this going out. All right? So whatever's happening in here, we have the particle confined. Okay. So two more things will happen here. Number one, why don't we do this? What if I look at this thing here and I say, okay, I'm going to start with an energy in which the energy of the state is larger than this V. All right, so maybe my particle's energy is going to be up here on this diagram. All right. That means the particle can occupy this side or this side, either way, but it could do so freely. Well, I mean, there's a potential cost, but that's okay. What that means is, if E minus V is positive, oops, let's get this lined up. Okay, so if E minus V is positive, greater than 0, then we expect standing wave solutions. Okay, if we have the top part going and the potential is infinity, meaning the wave function is 0, then these standing waves could be sines, sine kx. Okay, these should be sine kx's if this is true. If this is true, we know we have to go to 0 on the sides, and a cosine won't do that. So we know we're going to have sines. All right. Let me just do this over here. Gosh, what I really want to do is go underneath this and draw this thing. All right, well, I'll do that in a minute. So if E minus V is positive, then we have standing oscillating solutions. Okay. What if E minus V is less than 0? In other words, what if the energy of the particle was down here? Okay, what if it's down here? Well, then this is kind of an interesting situation, because here on the left side, the wave function is definitely going to 0. But over here on the right side, well, this is not an infinite boundary, and so it won't be going to 0 there. Okay, so we have to think about what happens if E minus V is less than 0. Then what happens? All right, let's talk about what happens. We call this side the infinite well, but when there's a boundary like this, we call that a finite well. Okay, and you could imagine that I could have a finite well that just drops in like this and comes out, and I've dropped a particle in here. Right? So maybe this is, say, V equal to V naught, and this is V equal to 0. But V naught is not infinity, so the question now is, what do these wave functions look like? Well, you'd like to think that the particle is confined, okay? You'd like to think that. And you would be correct, but with a difference, okay? We can no longer force the wave function to be 0 outside this well. We can't force that because V is not going to infinity in this case. If V is not going to infinity, then the wave function is not going to 0 quite as quickly, right? It's not equal to 0 in these cases. It has a value, okay? Now, we can see what that value is going to be, or I don't mean value, we can see what the function is going to look like. What's the wave function going to look like if we're outside this well? If we're outside the well, and suppose that we have energy of a particle in here, right? So suppose that the energy is here. That's our energy. So if I try to solve for the wave function outside the well, out here, E minus V is definitely a negative number, because E is low and V naught is large, and so this is true. If I mathematically look at this then, E minus V is negative, which cancels this negative. And then I end up with an equation that looks like this. The second derivative is equal to a positive number, 2m over h bar squared times V, I'm just going to call it V naught in this case, minus E, like so, times psi. All right, now I have the situation of I got to take two derivatives of a function. I got to still return the same function, but now I just get a positive coefficient multiplying the thing. Okay, what kind of function is this? Well, for those of you who are mathematically inclined, You probably see it. If not, let's take a quick look. This means that this is a positive constant. Let's call it alpha or something like that, or alpha squared because it's two derivatives. That means then that psi is going to be proportional to a e to the alpha x plus b e to the minus alpha x. If I take two derivatives of a regular exponential, I'll get the exponential back again, and I'll get a positive constant. Here the constant's already positive, here the constant's negative, two of them makes it positive. So in the first case where I have a positive e minus v, which results in an overall negative sign here, that gives me the oscillating solutions. That's an e to the I. That's an e to the I kx. This is just e to the alpha x, not an I in it, in other words. The I makes it the oscillating bits, right? That's the sines and cosines. This is just a dying exponential or an increasing exponential. Now, in the case of looking at the coefficients, like we did last time, we were able to, when we had this condition of the potential going to infinity and the wave function going to 0 at the sides, we were able to eliminate the b coefficient of the cosine, okay? We were able to do that because the cosine does not go to 0 at its endpoints. It goes to 1. We will be able to eliminate one of these also, and here's why. So this is exponentially increasing behavior. In other words, this is blowing up to infinity as x gets large, okay? This is dying. This is a dying exponential. It's decreasing and becoming 0 as x goes off to infinity, okay? So what we expect then is that as the, let's see here, let's go back to this one. As the particle has this defined energy, it's a well-defined energy. If I think about what the wave function should be doing far away outside here, far away outside here, do I expect to have larger and larger and larger probabilities of finding the particle in this region as I go further to the right? I hope you would say no. The particle should be fairly well confined. I should not be increasing my probability of finding it as I go further outside the well. The energy is lower than the well depth. So it shouldn't really be inclined to just hop on out of here and take off. I should not be finding high and high and high probabilities of the particle being here or over here. So what we do is we eliminate the increasing exponential, and we instead stick with the dying exponential. Problem. If I go to the right here, I am in the positive side of x. That means if x is positive, then I have a dying exponential. If I go to the left of this, I may have x being negative, but if I have a negative x in here, then this has suddenly become the increasing exponential, and this one has become the dying exponential. So we have to solve that by saying, I'm just going to imagine I'm not taking that one, but what I'm going to do here is I'm going to put absolute value signs on that thing. I'm going to change this to b e to the minus alpha absolute value of x, such that I'm guaranteed a dying exponential on both sides. Okay. So we are examining what happens if I have a less than an infinite potential barrier. And that's exactly what happens in this step case right here. This potential is some amount, some number, call it V naught. I don't know why I didn't do that before. I call it V naught here. Okay, same exact thing as in that one. And therefore, if the energy is lower than V naught, then I'm looking at exponentially dying solutions in the forbidden region. Okay? If I move back to this region and I want to solve for the wave function in here, well, I have no problem. Okay? If the energy is in here, call this E1. If the energy is in there, E1 minus the potential is a positive number. E1 minus potential is positive number, then we have standing wave solutions. Once I look in here, say this is region 1 out here, region 2A and 2B, and then region 3, like so. If I look at 2A, I should have standing wave solutions. If I look at 2B, I should have exponentially dying solutions. Once I get to region 3, I should have 0, just like in region 1. All right? So through doing that, we can start piecing together what does the wave function look like. Okay? So if E minus V is less than 0, then we have a dying exponential. All right? Then psi is proportional to dying exponential. Okay. Okay, I'm gonna take this out now. I'm gonna leave this because I wanna draw underneath it. Okay, so we've attacked these two things. A couple other things that I want to bring to your attention. We think about, and this should also go as a check mark here, so I'm just gonna continue my check mark list over here. Check mark is that psi squared is a probability. That means that the amplitude of psi is indicating what the probability is, okay? So when I draw, for example, something that looks like this for my wave function, let's say this, and then this, okay, if I'm plotting psi versus x here, if I have a tiny little peak here and a big peak underneath here, remember that if I want the probability, where's the most probable place I'm going to find the particle? Well, I have to square this in my mind and then look at the peaks. If I square this tiny little peak here, it'll become slightly bigger. If I look at squaring this huge peak here, it's going to become massively bigger, right? And it's going to flip over because it's going to be positive instead of negative. So I have to look at where the peaks are and how big are the peaks. Okay? Where the peaks are bigger means the particle is more inclined to spend time there. All right, so psi is a probability. What we're getting out from that is large peaks, whether or not they are positive or negative peaks. It doesn't matter, right? Because when you square them, they all become positive. Large peaks mean more time spent there. Okay? In other words, there's a higher probability of finding the particle here. That means it's spending, consequently, a higher proportion of its time here, rather than here or here. Okay? Now, reason I bring that up is back to this thing. If you are a particle, now, if you have E1, you don't really have a choice. You're pretty much confined into the left side of this. But if I have a particle with a E2 right here, if I look at a particle with this energy and I'm trying to construct its wave functions, which side do you think you might be more interested in spending time? The side where I have some potential energy left? Or can I go all the way down to the bottom and just have zero potential energy? Hopefully you can see it's going to be this side. Because things tend to try and usually you'll find things where there's lower potential energies. There you go, right? Are you going to sit on your couch or do you want to lie down on the couch? Right? The same basic question. This just gives the ability of the particle to lie down on the couch. Okay? So you would expect the peaks of the wave function on this side to be higher than the peaks of the wave function on this side then. right? As long as it's got that energy that's above both of them. If it's this one, it's not really going to spend a lot of time in this area, so we'll go over that too. But all right, something to think about. What else to think about? Here's another checkbox, or check mark. If you look at the kinetic energy of a region, so here the particle has a particular energy, whatever the energy is, okay? But in the case of the lower down here, the zero potential, all of that energy is kinetic, right? But when I go to the step, does it have that same amount of kinetic energy? Or does it have lower kinetic energy? Or higher kinetic energy? It has lower kinetic energy. Because of the total energy of the particle, some of it has to get used to be over here, just to be here. It's got to use some of that energy. So it has less overall kinetic energy left over. Okay? So the kinetic energy in a region is proportional to the momentum in that region. And therefore, if we're talking about the momentum, we are talking then about the wavelength of the wave function. Okay? Remember that lambda is h over p. And if I'm thinking classically, then I would say that the momentum is related to the kinetic energy by p squared over 2m, or the kinetic energy is related by square root of 2mk. Regardless of what the actual relationship between the momentum and the kinetic energy is, we know that there is a relationship between them. They are both concerned with motion. So it is generally fair to say, if something has more momentum, it will have more kinetic energy, right? For these particles, when their kinetic energy is higher in this side or lower in that side, they will have consequently higher momentum on that side, lower momentum on this side. Therefore, the wavelength should reflect that. Okay? Remember, if the momentum is higher, that makes the wavelength narrower, shorter. And if the momentum is lower, then that spreads out the wavelength a little bit. All right? All right, so with that in mind, let's take a look at some trial wave functions for this situation. There's also some other things that I want to impart. We'll probably talk a little bit more about this, but also think about the symmetry of the wave function and how it connects to things. So we already know the wave function should be continuous and things like that, but we also want it to be mirror symmetric about points, right? So if I take, for example, what's happening in the middle of this thing, it should be mirror symmetric about that. All right, so let's graph the wave function here in this potential, which goes to here and has a step right here. And so we already know that on this side, psi is equal to 0, and on this side, psi is equal to 0, because those are the infinite boundaries, okay? So this is my effective infinite well here, and I've got a slight step in the middle for a finite shift. All right, let's start off with the energy of the particle being E1. Okay? So this is the, maybe this is the ground state, who knows? Okay, from this I know a couple of things. Number one, I should have a standing wave solution in here, okay? I should have a dying exponential solution over here because the particle should not be found more on this side than on this side when the energy is lower than the potential. Okay, now classically, there's no, classically this is a forbidden region for the particle over here, right? There should be no probability of ever finding it over here because that would violate energy conservation. But what happens when I think about the the n equals 1 state. Suppose this is the n equals 1 state, the ground state. So I'm going to have a wave function that goes to 0 at the side here, and looks kind of like the n equals 1 state for the infinite square well that we talked about yesterday. In other words, just a jump rope. Remember that the number of bumps is the same as the quantum number. So this is E1, this is the ground state, so I have one bump. So that means I should have one bump, and it goes like this. But that bump is not going to 0 right away. No, it's not going to 0 right away. What's going to happen is I'm going to get this exponential piece that's going to continue the curve and smooth it down to 0, because when I'm in this region, I'm in a situation where I need a dying exponential. So I need to connect the dying exponential to my standing wave here in order to make the wave function continuous. So this part here, I'm going to make it kind of a longer tail one here, like this. Hopefully you can kind of see that a little bit. It should be kind of curved like this. Like so. All right. Okay, so in order to mark out what I want to think about, I'm going to communicate that and tell you that I have a standing wave solution here that is proportional to the sine of kx. All right? I'm going to have here a dying exponential proportional to e to the minus alpha x. So that's why I'm calling out these curves, so that I can give you some kind of mathematical basis. Hey, I know what these are. If you prefer not to use the mathematical notation, you would say standing wave, right? One node standing wave, dying exponential. And then that dying exponential connects to the 0 line, and it's 0 out here. So the wave function is continuous and has a value at every single point. Okay. So this is for the situation where the energy is less than the potential step here. What does this mean? Well, the probability of detecting the particle a little bit into the forbidden region is not 0. That's what it means. If I square this thing, I'm going to get a big peak. I'm going to find it mostly in here, but there is going to be this thing over here where I'm going to potentially find it over there. However, I will say this. Even though it looks like there's some probability here, it would violate energy conservation to be finding the particle here, right? So could we find it there? Well, not technically, no. Not technically, even though the wave function says there's a probability of it being there. It's kind of a dichotomy, and it's one that you kind of got to get used to. Let's take a look at what happens when we go to energy level 2, in which here I've got a much larger kinetic energy on the left side than I do on the right side. Okay, so now I'm going to keep my psi equal to 0s here, but I'm going to erase what's in the middle. And I'm going to plot it. And I'm going to try and take a guess at what I think the wave function looks like. So if this is the 2 state, then what I expect is something that looks like the 2 state of the infinite square well, which, as you might remember, is a bump up and then a peak, and then a valley underneath, and then a return, right? It's just a basic full sine wave. So I want to use that. That's why I'm saying I took time to solve the infinite square well, because we use that to that's our starting point. If I think of the infinite square well starting point at the n equals 2 state, it looks like a full sine wave. This is basically an infinite square well in the n equals 2 state, but then it's got this little hitch in it right here. So we have to start with the infinite square well state 2 and modify it to take care of the hitch, all right? So, let's think about this. In the n equals 2 state, where it has energy above the step height, what we want to think about is, all right, I know I want, say, a peak on this side and a trough on that side. One question is, well, how big are these peaks and troughs? So when I think about the kinetic energies, and I think about the probabilities, okay, I want to probably find a larger peak here. Okay, so when I think about the probability, I want to think about the probability of it is likely higher for it to be in here than it is over here. So I would think about a larger peak here. So let's try and sketch this out. This might take a couple of trials to do this, but nonetheless, I want to think about something that's got a higher peak here, like that. And then something that may have a lower peak on this side. But at the same time, am I sure I want this shape? Because, right, if I go like this for a lower peak, these two things, though, have the same wavelength. But that's not quite what should be happening, right? When I think of the kinetic energy in the region, where the kinetic energy, so this is, I didn't really finish this off, so this is proportional to, the wavelength of the wave function is proportional to 1 divided by the kinetic energy, say. Visually, where the kinetic energy is higher, I should have a smaller wavelength. And where it's less big, I should have a larger wavelength. All right, so I want to modify this because both of these have exactly the same wavelength, and that is L, if I go 0 to L here. It just so happens this one has a higher peak than that one does. Okay, so what I want to do is think about, well, if I want to make this a smaller wavelength, I have to shorten this in a little bit, right? I have to shorten this down a little bit. And then also keep this, this has more kinetic energy, so it's got to have a longer wavelength. All right, so thinking of the 2 state, I know there's a crossing in the 2 state where the probability of finding it is going to be 0, but the wavelength over here has to be shorter. So I have to look at something a little bit more like maybe that. Oops, that doesn't quite look like what I wanted. I missed that out a little bit. Okay, something maybe more a little bit like this, where it's got a higher probability here. It still has some probability of being in here. Notice that there's a 0 probability that falls not in the center of the well and not quite in the center over here, but a little bit more over here on the side. Kind of goes up and then falls in like that. Okay. The wavelength is longer where there is less kinetic energy. So I'm exaggerating this somewhat, but nonetheless, it's kind of a double hit because not only is it having less kinetic energy, so the wavelength is longer, but also there's less probability of finding it there, so the amplitude should be squashed down a little bit. All right. All right. Okay. Is there anything else I wanted to talk about? Not necessarily, but I do want to think about the mentality of knowing what the standing wave solutions for the infinite square well look like, and then taking them and slightly modifying them so that they work. So let's see if I can check my solution here. Let's see, can I get my... let's see if I can check my solution. Let's go to the, let's see here. If I go to this thing, okay, if I go to this thing, shorten that up a little bit. I'm going to choose a stepped well. Okay, and so here, yeah. So see, look what's happening. You have a slightly. Oh, I got that backwards. Duh. Slightly higher. It's traveling. Oh yeah, I got it backwards. So I should. So all right. Oops. All right. So let me show you this. We'll look at the wavelength first. Let's see here. No. I want to be above here. What am I doing? I want to be up here. Okay. So let's look at the wavelengths first. Okay, so the wavelength of the particle when it's in the lower side here, right, is about that much. Whereas the wavelength for the particle in the upper section here is, I think you can see that's visually longer, right? Is visually longer. Right, between there and there is a bigger distance than between here and here. If I look at the two, the peak to valley distance, all right? Okay, what I got messed up was the wavelength should be proportional to 1 over the kinetic energy, which that is going on right here. What I messed up was the probability. Larger peaks mean more time spent there. I got it backwards. So look, this has a larger peak, right? This has a larger peak than that does. And I forget that. What my mistake in this is thinking that if you spend more time here, you have consequently lower energy. But that's not necessarily true. What I messed up was in thinking, I should have been thinking of the kinetic energy. Okay, so on the side here in the well, where the kinetic energy is higher, the speed's higher there, right? The speed's higher there. So it's going to spend less time there because its speed is higher. What I forgot about was the changing in the energy, right? I'm not talking about the total energy. I should be talking about the kinetic energy when I'm thinking about time spent. So time spent means here with this energy, up here at 3.58 worth of energy, the kinetic energy in this side of the box is larger, and so it's moving quicker over here, and therefore slower over here, okay? If it's slower over here, you have more probability of finding it over there. That was my problem. I have more probability of finding it over here. This is lower because it's moving faster. We have lower probability of finding it over on the right side, in this case, where the well is deeper. So mine's backwards. Good, so this is why you check things, right? And you go, I can't find this exact state because they don't have the 2 state being up there. So the minimum state that I have, I could have that one. I could have just barely that one. That's the 3 state though. The 2 state doesn't start until I get down to here, and by then I'm already into the well. So our 2 state looks somewhat similar to this, right? Where there's a crossing over here on the side in the lower well. We had the same thing. But nonetheless, look at the exponential, right? Look at the exponential dying off here, okay? Look at that. So that's because the energy is this red line here, and you have probabilities of finding it over here. When the energy is less than the potential, it can't technically move over here, but there's a probability of it dying off out here. Alrighty, so that's what's going on here. Okay, so this is good. What I'm going to do is I'm going to modify my wave function slightly because I want the big peak to be here. I really actually want it to look more like that one. I want the big peak to be here. Okay, oops. So that means I've got something that looks like this. Longer wavelength, but bigger peak time. Because lower kinetic energy means less speed and therefore more time spent there. Darn, I liked that couch analogy too. I can't believe I messed that up. Anyways, oh well, it is what it is. So the idea being that you're still looking at the second state in the infinite square well, right? Which would have looked like, say, that. And we're taking it and modifying it by squishing the amplitude or extending the amplitude when necessary, and then squishing or moving out the wavelength whenever necessary. Okay. So these are some of the things to think about when you are looking at different potentials. Okay. Another one we can look at is one in which I take this barrier, but then I flip another well onto the side of it. So I make it still infinite in height. Okay, so it's still going off to infinity, but now I've got a bump right here. 1, 2, 3, 1, 2, 3, 1, 2, 3, and now it's going off to infinity. And this is height V naught, and this is height V equal to 0. And this is V equal to 0. What do you suppose the wave function looks like for this thing? Okay, well, once again, we need to know what is the energy of the particle. If the energy of the particle is, say, this, then it's going to be mostly confined in that side, right? If I say it's that, then it'll be mostly confined in that side. But if this energy is high up enough, my dying exponentials might connect a little bit. Right? If I have a particle energy which is way up here, then what I'm going to do is I'm going to have 3 situations. 2 of them will be the same. And one of them here, I should have, when there's a bump, I should have a larger peak because there's less kinetic energy, so more time spent there. And I should have a lower wave, I should have a longer wavelength, right? Because the kinetic energy is lower. So in the meantime, when I look at the wave function for this situation, I'm going to think, all right, well, if I look at this one up here, suppose, let's see, what do I want to do here? I want to do, let's say this is the 3 state, the n equals 3 state. So what I want to do then is take this to here and this to here. All right, so in these cases, if I have 0 potential energy here, all the energy is kinetic on the sides. If all the energy is kinetic, remember that means it's traveling faster, and so it's got lower amplitude, and higher kinetic energy means it's got a shorter wavelength. So it's going to have something, well, and of course it's 0 out here because these are infinities. So here's the edge of it, here's psi equals 0. All right, so here it's going to have something that looks kind of like this, short wavelength and lowish peak. Okay, this is for E3, for the n equals 3 state. So over here it's going to do the same thing. Short amplitude because high kinetic energy, short amplitude, short wavelength because high kinetic energy, and then also in here, large, oh, it should be centered, I could do it a little better than that. It should be a large peak here because it's got lower kinetic energy. Okay, it should be a large peak here because it's got low kinetic energy and a longer wavelength because it's got low kinetic energy. Okay, so the n equals 3 state, when the energy is above the V naught, would look something like that. I would not have any dying exponentials because the energy at all points is E minus V is always positive, which means I should be looking for standing wave solutions at all times. And this, what do you know, looks like the n equals 3 state in the infinite square well. It's just right? It's just modified a little bit. So that's what I mean. When we look at those standing waves, we should just be thinking of what do I need to do to the amplitude? What do I need to do to the wavelength? And it's the same basic shape. Okay. Alrighty, looks like we are just about out of time for today. So going forwards with that as best you can because of my mistake, which sorry about that, but hopefully I corrected well enough. The qualitative sketching of wave functions for different potentials. Okay, think about these two, and we're going to look at different energy levels for these two. And you can think of all sorts of other types of potentials. I'll give you a couple on the homework, on homework 9 to sketch and to try your hand at implementing these, hopefully better than me, and we'll go from there. So that's qualitatively how to look at what the wave function, what the wave function's behavior is based on a potential, right? And that's without solving the Schrodinger equation. So, good times. Remember, please send back lab kits. Please return lab kits. For those of you who've done that already, thank you. We need all those lab kits back. So we have a summer class and they're gonna need every single one of those back because we don't have a lot of money to keep purchasing more of these because they keep migrating away with students. Please send them back, all right? And we will be grateful for you doing that. So I will sign off at this point. We do not have any lab this week because lab is done. And that means I will see you on Tuesday of next week where we will start talking, we'll talk a little bit more about qualitative wave function sketching, and then we're gonna start moving into the functioning of a laser and possibly a little bit of radioactivity at the end of the class. This is the end of week 14, folks, so that means week 15 is next week, and that's our last week, so we have a couple of classes left. So we'll do a couple of interesting, fun topics, and then we're about ready to call it done for the semester. So, enjoy your weekend. I will be getting Celebration 2 back to you at some time in the next few days. So keep an eye out for that, and good luck. Have a great weekend, everybody. See you later.